mn at time 0, and then it will be multiplied by e to the power I omega mn t, right? And this omega mn was the transition frequency from the state m to state n. So E m minus En by h cross, right? So the terms in this matrix will be time varying, and this is obtained simply by obtaining the time non-varying terms at time t is equal to 0, and each term, depending on the location of each matrix element, mnth matrix element will have a different value here. Okay, so that is the concept. And if you have this difference between m and n exactly 1, that means here it will be omega h cross divided by h cross, and therefore it will be omega. So if it is just one step going down or up, then it will be omega. And then I showed that this the matrices will have this character, will have the character that there will be three sort of diagonal elements that will remain. X at 0, we are now doing it at x at 0. It will have some factor up front, which was calculated to be h cross divided by twice m naught omega, and then the matrix had the diagonal terms is 0. So why the diagonal terms would be 0? Because the if there is a transition from m to m, the value is 0. The energy difference is 0. So therefore the diagonal terms will be 0. All these terms will also be 0. Only these two, one step of diagonal elements will remain. And I showed that this will be root over 1. This will be root over 1. This will be root over 2. This will be root over 2. This will be root over 3. This will be root over 3, and so on and so forth. That will be the structure of the space. So let me write it here. And the P will have at the 0th instant, it will have square root of m naught omega h cross by 2, and then these terms, in order to make it a Hermitian operator, will have the character of the Hermitian. Again, the diagonal terms will be 0 because the x and p I showed to be proportional to each other. So if x is 0, the p is also 0 in the diagonals. These are also 0 in the diagonals. Only these terms will remain. But here, this will be root 1i. This will be minus then root 1i. This will be root 2i. This will be minus root 2i, and so on and so forth. So these were the structures. How did we arrive at that? Notice the line of logic that we used. At some stage, we arrived at an equation. Here. It was omega mn square minus omega square times x mn equal to 0. Now this implies that when this term is 0, then this term can be non-zero, and when this term is 0, then this, or when this term is non-zero, then this term has to be 0. Now when will this term be 0? That can be 0 only when omega mn equal to omega, and that essentially says that only when the difference between m and n is just 1, then only this term can be 0. Otherwise, this term will be non-zero, and therefore these terms will be zero, and that's why all these terms are zero. Get the point now?
Okay, sir.
Yeah. Now there was this formalism actually tells you how the state vectors, the state vectors vary with time, and how the operators vary with time. State vector in the uh, Heisenberg formalism will not be time varying, but these will be time varying. These are the operators. These will be time varying, and I have also shown that the basis vectors will be time varying. And if the state vectors rotate this way in the Schrodinger formalism and the basis vectors remain the same, they will have certain coefficients, uh, basically the projections of the state vector on the basis vectors. Now, when you go to the Heisenberg formalism, the state vector stays put, but in that case, the basis vector has to rotate in the opposite direction so that the projections remain the same, because projections are something that relates to something that's observed. Okay, projections indicate the probability of observing a particular eigenvalue. So that is the formalism of the Heisenberg picture. Clear? Can I go ahead? Okay. There was another reason why I sort of did these in a bit detail, because as you have noticed that the Schrodinger picture with which you have worked all your life, last semester and this semester, this and the Heisenberg picture coincides at t is equal to 0. Therefore, whatever I have obtained here, these are also true for the Schrodinger picture at t is equal to 0. And in the Schrodinger picture, the operators do not vary with time. Therefore, these matrices that I have obtained are also the matrices for the Schrodinger picture related to the X and P, and if you know these, you can also obtain the Hamiltonian, things like that, in the energy basis. So we have already worked out earlier how these operators look in the position basis. Now you know how these operators look in the energy basis. And the way you have solved the problems in the position basis, similarly, the problem can also be solved in another basis. Change of basis is not a problem. We do that whenever we find a particular basis more convenient than another. The assignment that you are doing now, that sort of, I could say, summarizes all that you learned in the last semester. Because if you have been able to do that, you are able to obtain all the eigenvalues. You have been able to numerically obtain the eigenfunctions, and you have also obtained the time evolution, and that's all about it. And you have seen how it can be done numerically. And this, what I'm just writing here, this also allows you another way of doing that, because when you are working in the, I'll just get some space and do that. When you are working in the X basis, then I say in the problem formulation that you take from, say, some value in the minus side to some value in the plus side. Probably it was minus 30 to 30, right? I forgot. And here is a 0, and we say that it starts with some Gaussian here, right? Now, why minus 30 to plus 30? Because unless you limit somewhere, the matrices will become infinite in size, so you will not be able to calculate. But also the reason is that beyond a certain range, the overlap of the given wave function with the position eigenfunction at different points, after beyond a certain range, they become practically negligible. And therefore, if they become practically negligible, it's not necessary to consider that. But after how much it becomes practically negligible, that is something that one needs to work out. Those who have worked it out, this particular problem, yesterday Gurpaul sent me a mail from which I could see that he has worked out and he has noticed the problem. See, the way we wrote down the del 2 del x2 term was in terms of a the numerical way of actually computing this. That takes into account the past value of the to the left side, the right side, and when you start the matrix, at that point you are unable to put what is there in the left side. So there are two error points at the two extremities of the matrix. They will not have much of impact if or they will start having impact only after some time. So you might notice that these look nice and fine Gaussian type wave functions, but after some time they will sort of develop wriggles. That is because of this numerical artifact at the two ends. How to minimize that? There are two ways of minimizing that. By increasing these lengths further so that the overlap becomes even small, where the problem are actually happening here, this extremity and this extremity, wherever the extremities are. Now, if the overlap is negligible there, truly negligible, then the effect will be very small. So in order to do that, you extend it and or both and stroke or you divide this into a larger number of compartments so that the matrix becomes larger to the extent that your computer can handle, and you can easily do that, and you will find that this does a nice oscillation this way and that, and yeah, visualizing the evolution of the wave function is a very important component of understanding quantum mechanics. Without that, all this algebra that you do, these you will forget after some time. I can tell you that. Unless you actually pursue quantum mechanics as your career, you will forget after some time. But what you will remember, what you will actually retain, are the visual impressions that you get. And this is a visual impression that in case of the classical harmonic oscillator, it just oscillates. It has a definite position. That position oscillates. In case of a quantum harmonic oscillator, a distributed function oscillates in the same way, but the spread actually changes while it oscillates. So these are the things that you uh, have to sort of presently you have to see, and that visual impression remains with you. Okay, and I'm sure that in doing this problem you had a lot of fun. Did you? Because by the way, I've posted in the We Learn page that I do not want anybody to be bogged down with the problem of creating animations. So those who have done it may post how you did it. Others can use that. So you only try to understand the the logic of this computation. And you can also do the same computation using these. Once you have these, you can construct the Hamiltonian operator, and the Hamiltonian operator's eigenvalues will be the energy values that you can observe, and so on and so forth. Only thing is that depending on where you start, where the starting when the starting wave function is, you will have to calculate its overlap with the initial with the different energy eigenfunctions in this case, and depending on that, you will have to do the computation. And if you find that beyond a certain energy value, the eigenfunctions overlap is becoming practically negligible, you can ignore that. So accordingly, your size of the matrix will be determined. Okay. Now, did you do this particular problem by actually what do you say? This method, Ci psi I e to the power minus I e I pi h cross sum over I, by calculating this, or did you do it by the time evolution operator method? Can somebody unmute and say? What method did you take for this calculation?
Excuse me, sir.
Yes.
So this method, this one which you mentioned.
Yeah. Then it would be also be wise to try out the other method. That will give you some further uh, both understanding as well as computation ability, because that will require a exponential of a matrix to be compared. Both MATLAB as
Sir,
well as
actually, I
SciPy
tried with the
has.
other method also.
Yes, again.
Uh, I tried with the other method also,
Uh,
like raising it with Hamiltonian operator. It wasn't working
it
properly.
wasn't
Like,
working.
no, I think NumPy doesn't allow it. Maybe I don't know. Maybe SciPy has the functionality, but NumPy doesn't.
Oh, you have
Maybe
tried.
I don't
You
know.
have tried that. I don't know what how the functionalities come in Python. I've done it using MATLAB, and where the instruction is that expm, uh, expm of the matrix. That's all.
Right.
Anyway, so
Okay.
try it out. You'll get some further. Okay,
Okay.
so let us go into today's material. We delete this stuff. I had talked about the Schrodinger picture and the Heisenberg picture, but there is one more picture that people use. That is called the interaction picture. Uh, well, you might have a question regarding when you use the Schrodinger picture and Heisenberg picture and all that. Uh, Schrodinger picture is something that you have been using most of the time. Uh, Next semester, probably you will get more opportunity to use the Heisenberg picture and the interaction picture. Uh, a typical setting in which the next semester will evolve is that you have a sort of unknown v function. By the way, uh, what program you have written so far for this particular assignment, that you can now apply to any v function, and you may simply see how the wave function evolves. Last semester you have learned the scattering and tunneling and things like that, right? So that can also be tried out using the same program. All that will happen is the v function will change. You have given a particular v function, now it will give different v function. You start the wave function somewhere, it will hit a wall, maybe a wall something like this, and then you'll see what happens. So the program that you have written is actually very versatile, and you can try out various things. Uh, Maybe I'll give some assignment to do that. But let us now go into this interaction picture. The interaction picture, or the generally next semester you will do much of it using what is known as the perturbation theory. That actually applies to situations where we are trying to calculate for an unknown v function. So if you have an unknown v function, a very common technique is to say that the Hamiltonian that we have now, Hamiltonian is something that is a bit complicated than what we have used so far, but it can be sort of seen as something that we know plus another component that we don't know. For example, if you have a Hamiltonian function which is somewhat close to what we already know, say the harmonic oscillator Hamiltonian function. So it can be written as a harmonic, a known part, which I will be calling H naught, plus another part, which is unknown part. It will be given the symbol H C prime. So this is something that is known and not time varying, and this part is something that is a perturbation. this can be time varying. This is a standard setting in which we do the perturbation theory calculations, and the interaction picture comes in handy. So therefore, I'll just give a brief exposure to what the interaction picture is. There, the formalism is somewhat similar to what we do in case of the Heisenberg picture, where your psi, in this case, I will designate by the I subscript, which will mean the interaction picture. It will be time dependent, but this will be formulated exactly the way we formulated the Heisenberg part. So it will be I H naught T by H cross. Okay, this was the operator times the Schrodinger picture psi. So what is the difference? The difference is that in case of the Heisenberg picture, this was the actual Hamiltonian. But in this case, we have broken up the Hamiltonian into two parts. One is the simpler part, another is the perturbation part, or this is also called the interaction part. So we are defining the psi in the interaction picture using only the known part. Okay, so this is time independent. This can or cannot both. I mean, it can be time varying. In some situations, the whole thing might not be time varying. So in that case, this part will also not be time varying. But any time variation will be incorporated in this part. So in the interaction picture, we have this as the definition of the psi in the interaction picture. What about the operators? The operators will be defined as A, I. In this case, these will be also be dependent on time. See, this, okay, let me write it, then I'll explain. This will be, again, defined by only the H naught part, the way we have defined. So it is AS was bracketed by U dagger U, and this U dagger U will be written as e to the power, in this case, it was I H naught T by H cross, and this was e to the power minus I H naught T by H cross. So here also we are defining it the way we did for the Heisenberg picture, and therefore what we achieved in the Heisenberg picture was that the psi function was not time varying. In this case, since we have left out this part, the psi function will be time varying. In the Schrodinger picture, the A was time varying, was not time varying. In the Heisenberg picture, it was time varying. In this case, also it will remain time varying. You might ask, what do we achieve by this? That we'll see in the next semester, but let us proceed a bit to see the characteristic of this picture. First important question is that how does the Schrodinger equation look in this picture? So the Schrodinger equation is I H cross, so I H cross del T of the psi function, but in this case we need to work out with the psi I, and this is what we have to work out. This is what we need to work out. What will be there in the right hand side. So if you have to do that, then I will have to just take a derivative of whatever we have in the right hand side with respect to time. So I H cross remains, and I take a derivative. There are two time dependent terms, so there will be two terms here. One is I H cross, the I H not will come out, by H cross will come out, and then the rest remains the same, e to the power I H not by H cross psi S T. The next term will be plus. This time we will have to take out the 11, right, IH cross. I will differentiate this, and this remains the same. So e to the power IH not by H cross, and then it will be ddt of this. Okay. So this I multiplied together will be a minus sign. H cross will cancel off. So it will be just a H naught times whatever we had, which is nothing but psi I. See, same thing. So psi I T plus this term will remain, and this term will be, I'll bring it here. So it is e to the power I H not P by H cross. I'll bring this here, I H cross ddt of psi S T, and this is something that we'll need to calculate. Okay. So let us keep it, because we have to figure out what this is, and then we'll have to substitute. So now we know that I H cross ddt of Schrodinger psi is the H operator operating on the Schrodinger psi. This was the Schrodinger equation, But now this is a combination of two components. Okay, so it is H naught plus H dash operating on psi S T. Then we will first operate with this, and then we'll operate with that. So what we ultimately get is it is H naught plus H dash psi st. I'll try to convert that into the interaction picture. Therefore, I have to bring this one to this side so that I can write psi s as e to the power minus that times t and this. So I'll be able to write it as e to the power minus I H naught t by H cross, and here it is psi I. I've converted that in terms of the psi I. Okay. So then I can substitute this here. So this equation now becomes I H cross d dt of psi interaction P is, first I have to write this term, minus H psi I T. Then I substitute this. If you substitute this, it becomes if I substitute this, I'll get there was this term already. Okay, so I have to write that first. Plus e to the power I H not T by H cross. Then I have to substitute this. It is H plus H naught plus H dash e to the power minus I H naught T by H cross, then psi I T. Okay. Now now I can break it up. If I break it up, that means once using H naught, another times using this, then it is minus H naught psi I T plus, it will be this term times this times this. Now, since H operator is commutes with any function of H, therefore I can bring this to this side and this to cancel off. So I get only H psi I T, which actually cancel off, leaving us with this term e to the power I H operator T H naught operator T by H cross H dash e to the power minus I H naught T by H cross psi I. Okay. If I notice what we have achieved is that the left hand side looks like the way the Schrodinger equation would look for the interaction picture psi. In the right hand side, I have this whole thing operating on the interaction picture psi. Therefore, if we define the interaction picture psi, interaction picture Hamiltonian as e to the power I H not T by H cross sandwiching H prime e to the power minus I H not T by H cross, then we have the simple Schrodinger equation in the interaction picture as I H cross del T of psi I T is equal to the interaction picture Hamiltonian operating on psi I, exactly the Schrodinger equation. Okay. So this is the advantage of the interaction picture, that we have a differential equation that is the same as the Schrodinger equation. Only thing is that we have suitably defined the Hamiltonian of the interaction picture. And this actually satisfies the definition of an operator that we have given, right? So like any other operator, the Hamiltonian operator also transforms in the interaction picture like that. But here it is only the interaction part. It is not the whole Hamiltonian, it's only the interaction part that appears. Now you might notice that if in the formalism, whatever we have written, if this part is absent, then this whole thing boils down to the Heisenberg picture. Exactly the same. So here we have only additionally kept this part. Additionally. And when you come to the perturbation theory computations, you will find that this offers a lot of advantages in comparison to the Schrodinger picture or the Heisenberg picture. That's why most of the the calculations in the next semester might use this formalism. Well, all that remains to be seen is uh, how do the AIs, any operator AI in the interaction picture vary with time. So what we'll do is we will take a derivative with respect to time, and our AI, let me write again, so otherwise you might not be able to do this because I've erased that. It was essentially e to the power I h naught t by h cross a Schrodinger e to the power minus I h naught t by h cross. This is what it was. So we are trying to figure out what is the derivative of that. The same way as we did for the Heisenberg picture. So when we take the derivative, there are three terms which could potentially depend on time. This may or may not have a explicit dependence on time, but we have to keep that possibility. So first we take a derivative of this. It gives I h naught by h cross. Then the rest remains the same. E to the power I h naught by h cross a s e to the power minus I h naught t by h cross. First term done. Second term, I will differentiate this. So plus the other terms remain the same. I h naught t by h cross a s remains the same. Now I have to bring out minus minus I h by h cross. This will come out, and then it is e to the power minus I h naught t by h cross. And the third term. The third term is plus e to the power I h naught t by h cross. No, I'll take a derivative of this. Del as t e to the power minus I h. Okay, now I will see that this term, these two terms can commute because both are dependent only on h naught. So I can bring, keep the I h cross as the common term, and it is e to the power I h. It will be then. I can keep the h naught here, right? For now, I'll keep it here. It was here. Let me here. As e to the power minus I h cross. This term is something that we know is AI plus here this one I can switch positions so that this becomes A. So e to the power there's a minus that comes out. So let me the minus here. There's a minus that comes out. Minus I by h cross comes out. Then here it is e to the power I h not t by h cross, first term down. Then I have the as term. I will change the position. So it is e to the power minus I h t by h cross. And then I'll put h. And this term is also known. So it is clear. Oh, plus here I have. Plus whatever was del as del t, that is now because of this converted to the I representation. And these ones I know, these are a I. So it is clear that it is I by h cross, it is h not ai minus ai h naught plus delta as del p in the I representation. So this is obviously, normally it is customary to write ai first, so I'll put a minus sign here. Minus I by h cross is the commutator of ai and the Hamiltonian plus the, if there is any explicit dependence on time, that will remain. And if there is no explicit dependence on time, it's only this. So it is d dt ai. So how does the ai operator change with time? It changes exactly the same way as it did in the representation. If there is no time-dependent term, this term also was there in the Heisenberg representation. So here also it remains practically the same as the Heisenberg representation. We only have to use the operator in the I domain. Right? Effectively, the interaction picture is sort of a intermediate between the Schrodinger picture and the Hamiltonian, the Heisenberg picture. And this will prove to be more useful in many applications in the next year. This year will not use it. This is sort of a prerequisite for something that comes.
Let us see the result obtained by some students in their submissions of the assignment 2. Well, you can see that here the wave function starts in one side, a narrow wave function, and then when it comes to the middle it widens, and again it becomes the mirror image of the initial one as it goes to the other side. This result has been obtained by many other students. Let me show one more. So here also you can see it has been done a little fast, but nevertheless you can feel what is happening. Some students have pointed out that they have observed a phenomenon that if it starts with a relatively wider wave function in one side, then it becomes narrow when it comes to the center. But if it is a narrow Gaussian when it is one side, then it becomes wider when it comes to the center. And in between there is one case which is just the Gaussian function shifted to the to one side with spread equal to 1. Then it remains the same shape as it oscillates from the left side to the right side. So this is the result obtained by one student, where the blue one is a narrow Gaussian in one side, it becomes a wide Gaussian when it comes to the middle, again a narrow Gaussian when it comes to the side, and here the middle one, the red one, is remaining of the same size and shape, while the yellow one actually was a wide Gaussian in the one side. It becomes narrower as it goes to the middle, yes, and it again becomes wider as it goes to the side.